How does an escalator haul 140 people up an incline as steep as Mount Fuji? What gives a handheld leaf blower the power to whip up hurricane-force winds? And how does a tape measure cram 5 meters of precision steel into your pocket? To answer these mysteries, we dive deep inside these and other extraordinary machines to reveal the secrets of how things work. The escalator, one of the hardest working machines around. At one of London's busiest metro stations, it shifts up to 13,000 people an hour all year round. But getting caught in such a powerful machine can cause serious injury. So how does it lift more than 100 people at a time, smoothly and safely? More than 10,000 moving parts work together. A tough steel cage on the outside takes the weight of 30 armored tanks every hour. 157 aluminium steps travel so far in their lifetime, they could go to the moon and back, yet always stay level. A heavy-duty electric motor can lift the weight of 2 elephants. This is a multi-million-dollar workhorse, powerful and built to last. When full of people, this escalator weighs 54 tons, the same as 18 SUVs. So it's got to be incredibly tough. The key to its strength lies in the way engineers build its frame. At this 15,000 square meter factory in Illinois, the frame starts life as 11 centimeter thick steel beams. Workers cut these to precise lengths, up to 1,500 per escalator. Crack welders then turn this pile of metal into a huge reinforced cage called a truss.
This unit's 104 foot long. You gotta have good, strong welds.
Butch makes the panels that form the truss sides and base.
I love welding. I started here in January of 1973. Been welding 37 years. These diagonal pieces actually keep it solid. That's why you see so many of them. Yeah, we make them as tough as possible here.
But being tough isn't enough. Workers must fit these side panels together to form a rigid cage with supreme precision. Otherwise, the stairs could jam. So they hoist the panels into a huge metal guide frame.
That feels real good right there. This yellow fixture, it has a series of plates along one side that are all set in line straight. And when we put a side on up against these stops, we'll put big C-clamps on like that. That's the key to getting a true straight escalator.
The end result? A giant steel cage, accurate to within a few millimeters all the way down, and strong enough to lift 140 passengers in a single ride. So how does it pull such a huge load? Hidden under the top of the escalator, a giant electric motor works round the clock. Inside, 2.5 kilometers of copper wire and a huge electric magnet spin a drive shaft 700 times a minute. This powers a set of cogs that gears down the revs and locks into a 6 centimeter thick chain. The massive drivetrain pulls the steps upwards at exactly the same speed, no matter what the load. The steps are part of a hugely complex mechanism. Any big bumps or vibrations could knock passengers over, and it's a long way down. The secret to making sure that doesn't happen lies in the way workers put them together, by hand.
We just take pride in what we do. You know, I build it as if it was mine.
Tab fits the drive chain and steps on some of the biggest escalators in America.
The escalator itself will have a 77-foot rise, so that's almost 8 stories. The unit is 188 feet long. The steps are attached to the chain with step pins put together correctly. With the dimensions set properly, the escalator runs smoother. Clear!
The steps themselves also play a big part in making sure passengers don't feel any bumps in their ride.
This escalator, once it's completed and installed, will have 269 steps. A lot of steps. Each step has 2 sets of wheels. It's our trail wheel. It rides on a piece of flat track that keeps everything in line so it can rotate around the escalator virtually rub-free, noise-free, and safe.
This flat inner track solves one of the fundamental problems of escalator design. Keeping the steps and the people on them level all the way up. So how do steps form a rigid staircase on the slope, then collapse into a flat platform so people can get off? The 2 sets of toughened plastic wheels on each step run on completely different tracks. The front set hooks up to the drive chains moving the escalator. The rear set locks onto the inner track. As the steps rise, the tracks draw close together and tilt the steps to form a staircase. At the other end, the tracks move apart again, so the steps make a platform and you can get off. But the combination of moving metal with lots of power has a flip side. Getting caught and dragged into an escalator can cause serious injury. So the first rule of escalator design is safety.
It hurt you. We don't want that. We want everybody to be safe getting on and off our escalators we build.
Sean installs one of the most important safety features, the comb plate.
It's a key safety feature of anything getting sucked underneath. Yeah, but everything needs to be square.
The comb plate protects one of the most dangerous parts of an escalator, where you step off at the end. Here, a moving step meets a static landing plate. If this trapped clothes or shoes, it would be disastrous. But this almost never happens thanks to the way the comb plate meshes with the deep grooves in the escalator steps.
Well, the steps got the grooves in it so it could line up with the comb plate segments. So any type of debris that's in a crack, they're gonna ride up on top of the comb.
It's a simple system that keeps passengers safe. And it's the reason all escalators have grooved steps. Once everything's installed, it's time for a full-speed test.
At this point, we are running it as a final checkout, making sure there's no noises, no pops.
Shannon makes sure every escalator runs as smooth as butter.
We have to make it as smooth as possible. You've been here long enough, you'll feel that something's not right, and we'll correct this, make it as quiet as possible before it even goes out the door. And if you're riding on an escalator, you don't want to hear noises. You definitely don't want to hear noises.
The steps are running smoothly, so this escalator's ready to ship. Across Europe, over 75,000 escalators transport millions of passengers every single day. We walk all over them, but these unsung heroes work long hours, pulling tough loads to keep our subways, malls, and cities moving. The leaf blower. How does a machine you can easily hold in one hand blow air at twice the speed of a hurricane? Under a tough polymer casing, 230 parts work together. a super light aluminum alloy engine with more power per kilo than a dirt bike, a fan wheel with toughened blades that suck in 12,000 liters of air a minute and ram it through an aerodynamically shaped nozzle to create the perfect storm in the palm of your hand. Generating winds this strong is a formidable engineering challenge. In this 36-acre factory, it all starts with the way engineers build the fan wheel. This tough part is actually made of plastic.
These are the plastic pellets that create the actual fan wheel. It obviously has to endure a very violent condition, and at 10,000 RPMs, you don't want shards of plastic launching around.
Marco knows pretty much all there is to know about making things out of plastic. If the fan wheel shattered when spinning, shards could fly off at serious speed. To make sure this doesn't happen, Marco uses a top-secret blend of plastics for strength. Moisture in the air can weaken the part, so he runs the pellets through huge dryers, then pumps them to plastic injection machines. These heat the material to melting point, over 200 degrees, then inject it into a metal mold.
This is the fan wheel as it is in the mold. The plastic is injected on this end of the runner.
A robotic arm picks up the scrap, while the finished fan wheel rides a conveyor to where it's checked for flaws.
The toughest piece of plastic we produce.
This looks nothing like a normal fan blade. So how does a small disc of plastic whip air into a mini tornado? With the engine at full blast, the fan wheel spins nearly as fast as a jet engine. Every second, its S-shaped fins scoop up 200 liters of air. They squeeze it sideways into a snail-shaped casing and down a narrowing nozzle, thrusting it out of the end at 260 kilometers an hour. The leaf blower's nozzle doesn't just direct the fast-moving air, it also actually increases its speed. The secret to how it does this is the unusual way engineers construct it, using the power of air itself.
Each one of these machines runs approximately 2,500 parts per shift, which would be 5,000 pieces per day.
Tim runs machines that inflate the nozzle like a hot plastic balloon. A molten tube drips down between two specially cooled metal molds. When they clamp together, a hollow metal pin blows air into the tube of hot plastic. The air forces the plastic out into the shape of the mold.
Once the mold opens up, the blow pin retracts, strips the part off of the blow pin, and drops on the conveyor belt for the operator.
Workers then trim the nozzle to size. The end result is a tough tube with a perfectly smooth interior that narrows towards the tip. As the air blasts down the nozzle, it's forced into a smaller and smaller space. This actually makes the air move 10% faster. Moving air at these speeds takes a powerful engine, but building a motor that is light enough to hold in one hand is a big engineering challenge. A ruggedized aluminum alloy casing cuts down the weight. At the heart of the machine, a single piston the size of a chess piece pumps like crazy. It fires on every turn, twice as fast as the engine on your car. This tiny powerhouse weighs as much as a carton of milk. but packs more punch per kilo than a monster truck. The quest to reduce weight doesn't end with the engine. Every single component inside this machine must be as light as possible.
Being a handheld blower, we're always thinking about lightweight.
Brian runs the assembly line that turns boxes of components into a finished machine.
The inner fan housing is your main support, kind of like the component that everything else would be attached to.
In a car, the engine is bolted to a metal frame for strength. In the leaf blower, it's bolted to a housing made of lightweight plastic to save weight. When they come off the production line, these units are ready to blow. The end result is a tough, powerful, and lightweight machine. A tiny hurricane you can hold in your hand. The humble tape measure is cleverer than you might think. How does it squeeze 5 meters of precision-engineered steel in a package that fits in your pocket? Under a toughened plastic case, 26 components work together. A tightly wound metal blade with super accurate markings. A rocker that can lock the blade without breaking it. And a tightly wound spring that retracts the blade in a fraction of a second. It is 5 meters of pure precision that fits in the palm of your hand. The key to an accurate tape measure is the way workers make its metal blade. In this UK factory, the blade starts life as a long strip of hardened steel. Workers wind it onto special cartwheels that weigh 130 kilos each and roll them to a custom-built painting machine. This paints the steel bright yellow to make the black markings easier to read. Next step, a digital printer marks out the numbers.
This prints all size blades from 2 meters to 100 meters.
Anita makes sure the printed markings on every tape are accurate. It's a big responsibility.
If it's out, then whatever you're building won't be straight. So you'll end up with sort of a shelf like that, or a house, or whatever you're building, it'll be all wonky.
The painted tape runs through a series of rollers up to precision print heads less than 1/4 millimeter wide.
So we have 3 black heads and 3 red heads, and it spray jets very, very finely the image, whatever you're printing, onto the blade.
The end result, markings accurate to the width of a human hair. But it's no good having a super accurate tape that you can't carry around with you. So how do you neatly coil up 5 meters of steel at the touch of a button? The end of the measuring blade hooks onto a soft metal strip. That's almost as long as the blade itself. As it coils around a central hub, it turns into a powerful spring that winds more tightly as the blade slides out. But release the lock, and the spring recoils to retract the blade in the blink of an eye. Getting the tension of the spring right is crucial. Too little and the tape won't retract. Too strong and it could hurt the person using it. So workers tailor-make the spring to the specific length and weight of each blade.
This machine makes the springs, which goes in the tape measure, which gives it the power. There's so many different components going into one tape measure that it's not as easy as it looks.
John's made tape measures for 27 years. The steel runs around a narrow metal rod at the heart of this machine.
And I run some through, chop it, put the auto on, and away you go.
This produces a curl, just like running ribbon over a ruler.
That's the first thing that goes into the tape measure, is a spring.
Workers mount the spring into a special machine that winds it onto a central pin inside the tape measure's body. Final assemblers install the rest of the internal components before the quality controller attaches the blade. But the tape measure has one final trick up its sleeve. Designers make the tip so it can move backwards and forwards. When hooked over something, the tip extends so the blade only goes up to the edge of what you're trying to measure. But to measure an inside edge, the tip retracts so the end of the tape butts right up to whatever it's measuring. We take this mini machine for granted, but millions of handymen and women across the world couldn't do without the breathtaking precision that fits in your pocket. The safe. These timeless machines are some of the toughest around. How do 21st century safes keep thieves out and even protect your valuables from a raging house fire? More than 500 super strong parts work together. The outer shell is a sandwich of ultra-tough steel and slabs of ground-up rock, fireproof to 650 degrees. 26 hardened steel bolts clamp the door deep into the sidewalls. And a lock with 1.2 million possible combinations gives easy access, if you know the code. The secret to what makes the safe so strong is the way engineers make its steel skin. In this 28,000 square meter Utah factory, the safes begin life as 9-ton rolls of coiled up steel. It's 5 times thicker than the steel used on car bodywork and incredibly tough. So how do workers wrestle this super strong steel into a precision-formed box? It's a mighty engineering challenge.
So this is the punch station. This cuts all of our holes and our corners out.
Thomas runs the line that turns thick steel plate into a precision-made box. In his line of work, speed is key.
This is the first part of the whole line, the whole system. Even with me having to stop for 10 minutes, it can cost the line 20, 30 minutes down the road.
A huge hydraulic press stamps the sheet of metal into a carefully designed pattern. A giant roller turns up the edges for added strength, before a robot folds the whole thing into a box. Thomas then welds the corners tight.
The only seam we have is on the one side here. You don't have a bunch of seams all over the place that can fail. This is going to be stronger than even having a weld on it because it's still connected all at one piece.
High-temperature robotic welders then attach the back plate. They melt the steel together to make the strongest possible join. Finally, workers grind off the excess metal from the welding. This leaves a super tough shell that's incredibly hard to break into. But a safe is only as strong as its weakest point, the door. So how do you make sure thieves can't simply force it open? The door on this safe has not just one bolt, but 26 toughened steel rods. They are even harder to cut through than the door. An intricate series of levers links the bolts together, so all 26 of them open and close at the turn of a wheel. To make sure this complex lock mechanism works properly, engineers install every piece by hand.
This is the spindle that opens up the safe. I'm going to assemble this before we mount it onto the safe.
Derek builds the sophisticated bolt mechanism. He must put together 94 intricate components in exactly the right order, and he's got to do it perfectly. Someone's valuables are at stake.
Just going to tighten this down so I can hold the pins in place. For the top and bottom pins, you have 4 on top and 4 on the bottom. Yeah, we're just trying to make them so they're all about flush with the bolt guides. These are the biggest pins that we have. They're 1.5 inches rather than the 1 inch. So as you rotate the hub on the outside, it moves all 26 pins into place.
Making sure that no one other than the owner can use this bolt mechanism is the next big challenge. To do that, the safe has a combination lock. This complex mechanical puzzle has over 1 million possible codes, but only one solution. The dial on the outside turns 3 notched brass wheels. Each correct number locks one of the wheels in place. Get all 3 numbers right, and the notches in the wheels form a gap. A bar now slots in and engages a lever that lifts the lock from the handle wheel. This releases the bolt mechanism so you can open the safe. This lock is incredibly hard to crack, but thieves aren't the safe's only enemy. It has to protect your valuables even if your house burns down. To do that, workers line the entire safe with heat-resistant sheetrock.
Basically, my job is to keep this steel box from turning into an oven.
TJ fits out the top-of-the-range safes. First, high-pressure water jets cut the board into a series of interlocking sheets. Then TJ puts this jigsaw puzzle together by hand.
The point is to get as much coverage as possible. Any gap is, a weak spot.
More layers mean more protection.
We've got 4 layers in the back. There's 3 in each side and the top.
Now this safe can keep its contents cool in a full-blown house fire for 2.5 hours. Finally, workers fit the shelves and inside lights. The safe is now ready to be the first and last line of defense in households all over the world. Thanks to clever design, this tough customer has brains as well as brawn. With more than 1.5 million burglaries in Europe every year, you never know when you might need one. Playing tennis takes 2, unless you've got one of these machines. How does the tennis ball launcher fire a tennis ball at 150 kilometers an hour every single second with pinpoint accuracy? Over 300 rugged components work together. A hopper full of 300 tennis balls feeds in 1 ball every second. A pair of powerful electric motors spin 2 super grippy launch wheels 4,000 times a minute. Precision gearboxes hook up to an electronic brain that gives impeccable aim. It's a tennis pro in a box. Accelerating a tennis ball to top speed in just 2 milliseconds without swinging a racket is no simple task. The secret lies in the way workers build the fast-spinning wheels at this family-owned factory in Los Angeles. These plastic engineers are some of the most experienced in the business.
Well, my dad started it in '64. Well, I've been here since junior high, probably since I was about 14.
Steve makes each wheel out of 2 very different materials.
We run the outside first, which is these.
He preforms the wheel rim out of a mix of rubbers to grip the tennis ball tight, then loads it into a metal mold. The machine injects molten glass-reinforced plastic. This fills the rest of the mold and sticks to the rubber. The end result, a solid wheel made from 2 materials. A rubber rim for grip and a tough plastic core for strength.
It flexes and has gripping power on the tennis ball, so it throws them more accurately.
So how do these super grippy wheels accelerate a tennis ball quicker than a launching rocket without shaking the machine apart? The secret sits at the heart of the machine. 2 electric motors drive the launch wheels in opposite directions. High-speed bearings help them spin faster than the rotor on a helicopter. A banana-shaped ramp feeds in the balls. They squash down to half their normal size and shoot out faster than a freight train. This machine will run you ragged without ever breaking a sweat. But spinning wheels at such speed causes problems too. All wheels have tiny weight imbalances that make them shake from side to side noisily when they spin quickly. It's one racket you don't want on a tennis court.
What I'm doing right here is just measuring the wheel. The wheel is really unbalanced right now.
Jose makes sure all the wheels run smoothly. His machine measures how much the wheel wobbles and where the excess weight is. His aim is to get this gauge to read less than 1. To remove the weight, Jose simply drills holes in the wheel's rim.
Your machine is telling you where to drill. We have to drill between 6 and 7 on your right-hand side. This is the process that we have to do over and over again. Maybe 4 more. This is what we want. And it should be ready to go into a machine.
Once balanced, each wheel runs perfectly smoothly, making it quieter and more accurate. But tennis isn't all about how fast you can hit the ball. This machine has to fire the ball into different parts of the court with pinpoint accuracy and mix up the shot styles. The launch wheels can swing in any direction, like a gun turret. To guide them, 2 motors connect to 2 precision gearboxes. These reposition the launch wheels in a single second to hit balls into every corner of the court with deadly accuracy. The launcher rarely shoots a single ball out of court. But making this machine so accurate takes time and skill. Workers assemble and test every aiming mechanism by hand. They even have a special name for it.
This part of the machine is called the guts.
Douglas has assembled tennis ball launchers for 15 years. But guts are no good without a brain. So Douglas must calibrate the computer that controls where the ball goes and how fast it fires to train this machine to play like a real pro.
That's a motherboard, the one that runs the whole thing. It simulates a player. This is where the fun begins.
Douglas lines up the machine with markings on the factory floor. It should hit the black line in the center of the back of the net.
Right now it's shooting it to the right. I would have to shift the pod to the left. I think it should do it already. It should be centered. Let's give it a go. There you go. Straight.
This machine will now fire balls anywhere in the court with pinpoint accuracy. It can play with topspin, backspin, and even hits a pretty mean lob. The tennis ball launcher is an unsung marvel of modern ingenuity. The perfect partner. It doesn't tire, it's there when you need it, and it never criticizes your serve. The music box. This is a 21st century version of a timeless mechanical marvel. So how does it play beautiful music at the touch of a button without electricity? An orchestra of 329 highly tuned parts work in harmony. Over 5,000 microscopic pins on a brass cylinder carry the code for 8 minutes of music. A metal comb with 92 sharp teeth tuned to perfect pitch. Powerful springs give extra long playback. And a tiny mechanical conductor keeps a steady tempo to make music with that special metal magic. Every one of these tiny pins has to pluck the right tooth at the right time. The secret to how they do this lies in the way the maker builds its intricate brass cylinder.
Music on a cylinder is defined by the location of all the pins. Every note has its own pin. So in this case, I need to accurately place 5,000 pins in a brass cylinder in order to play that musical program.
Jonathan Hertz is a master music box maker whose creations are unique. He works out of a small shop in his backyard in Vermont.
Nobody other than myself makes a music box which is an actual reproduction of 19th century golden age music boxes.
The music boxes may be historic, but Jonathan's tech is straight out of the 21st century. While his predecessors put these pins in by hand, Jonathan has built a computer-controlled machine to do it all automatically.
The computer knows the location of every note in the tune, and this is the machine that selects that location on the cylinder, drills a hole there, and inserts a small piece of music wire into that hole.
Each tooth on the comb of a music box plays a single note. As the cylinder rotates, the tiny pins pluck the teeth as they move past. So Jonathan must position each pin precisely to play the right note at the right time.
There are very subtle changes, tempo and timing, that the human ear can hear that is measured in tenths or even hundredths of a second. And with this slow-moving cylinder, the pin needs to be located within just a couple of thousandths of an inch.
The pins on a music box don't just play one song, they play 8. This is how they do it. Each segment of the cylinder carries 8 rows of pins. Each row plays a different tune. When a song ends, a tiny cam rotates 1/8 of a turn, shifting the cylinder sideways just 0.4 millimeters. The teeth of the comb now engage with the next set of pins, which play a brand new track. To turn the cylinder at all, the music box needs power. It runs like clockwork without electricity thanks to the way Jonathan installs the main springs. The springs may be small, but loading them can be dangerous.
This spring has enough energy in it to, should it fly apart all of a sudden, cut right into flesh.
The main springs start out as flat, flexible 1.8-meter pieces of metal. Jonathan must coil these up into a space just 6 centimeters wide.
Once it's in the spring barrel, it's completely safe. It will never fly out and bother anyone, but until then, it is a potentially dangerous storage of potential energy and sharp steel. There we go. This provides all the energy that the music box uses when it's being played. We wind it up by turning the shaft, and it unwinds by turning the cylinder.
The coiled springs store a lot of power. To make sure the cylinder doesn't spin out of control, a mechanism called the governor uses air resistance to keep it in check. This is one of the most important parts of the whole box.
If, for any reason, this governor fails, the cylinder would spin extremely fast and destroy both the pins on the cylinder and the teeth of the cone.
The gears spin the governor 1,000 times faster than the cylinder itself.
That fast rotation makes big wings beat against the air. The faster it goes, the more wind resistance these fan blades generate.
This acts as a brake on the fan blades to stop the cylinder from spinning out of control. This handcrafted music player is a masterpiece of precision engineering. And thanks to 21st century technology, enthusiasts all over the world can still enjoy the old-fashioned sound of metal on metal. The mighty Escalator, the tape measure, the security safe, and the music box. What's inside isn't always big, but it is clever. Next time you see one of these machines, remember, there's more to how it works than meets the eye.